let's continue on this chapter on distributed forces. So until now, when we consider rigid body, yes, the equilibrium in rigid body, we consider that all the mass is distributed evenly throughout the geometry of the structure. So in that case, the center of gravity is usually will be the same as the center of the geometry, as the centroids. The centroid is the center of the geometry. The center of gravity will be the same as the centroid. Okay. For rigid body, we have assumed the attraction by the Earth is represented by a single force applied at the center of gravity, because the mass is distributed evenly throughout the geometry of that structure. That is why then the weight is applied at the COG, at the center of gravity. However, in reality, then the mass is not usually evenly, uniformly distributed over the entire body. The left part may have denser mass compared to the right part, for example. So it means then the center of gravity will not anymore be at the centroid. The centroid is from the geometry only when we consider only the geometry. But the centroid, we also consider then the density of the mass of that structure. Okay. So, for example, here, let's say in the first part, on the upper part, rectangular shape A, the assumption is that the weight only is happens at the center, one only single weight at the center of that mass. However, in reality, the weight is distributed, yeah, across all the cross section of that shape of that structure. Similarly, when we have B here, we assume here always a single force, yeah, until now, yeah, a single force at the center of gravity of B, but in reality, it is the summation, the sigma of distributed forces along the surface that are interacting with the other surface, the other body. Okay, so we have three categories of distributed forces. One which is called as the line distribution. Yeah, so here the force is distributed along one dimension of geometry. Number two is area distribution. The weight is distributed across two-dimensional surface. Then we have volume distribution. The weight is distributed along the three-dimensional volume elements of that structure. Let's have, let's consider this case study one. A homogeneous rod of length 1 is made of aluminum. Aluminum here. The centroid, and so since it is homogeneous, then the centroid and the center of gravity, COG, will be located at the middle point, the same point. Yeah, COG and centroid, the same point. Centroid is the center of the geometry. However, on the second case, we have a second homogeneous rod of length 1, yeah, which is the same length as the previous case. However, it is made of two parts of equal length, but half of it is aluminium, and the left part, the second part, the right part is made from steel. The second half of the right is made of steel, and steel is basically heavier than aluminium. The centroid, the center of geometry, is still located at the middle point. However, the center of gravity will not be located anymore in the middle point, because the right part, composed from the steel, is heavier than the left part, which is composed from aluminum. That is why the center of gravity will shift towards the right part here. Okay, so this is the middle part is still the centroid, the center of the rectangular geometry. However, the center of gravity will shift to the right. Another case study in 2D analysis. Consider a homogeneous plate with a uniform thickness, as shown in this figure. How can we determine the center of gravity of this plate? If this is a two-dimensional plate. The plate is homogeneous and has uniform thickness. So the centroid and the COG will be the same point. But since this is irregular, yeah, How can we determine the centroid as well as the center of gravity? So the procedure is mark a point on that plate, hinge the plate about that point. So we mark a point and then we hang it. Hinge, hinge means become a rotational axis. Like this one, we draw a vertical line passing that point. We shift it and then we do another point. So the intersection of these lines become the centroid. Okay, the more we draw, the more accurate the centroid will be. So that is the method how we determine the centroid of areas and lines. So the scope of this subject covers the ability to solve application rather than derivation of the problem. The derivation problem, we are not deriving the formula. So we, in this case, we are just using the formula obtained from solid mechanics. If you are interested, why the centroid or center of gravity of certain geometry is this way, please refer to solid mechanics book, solid mechanics textbook. So for example, we have a triangular. Okay, in this case, the area is equal to the bottom part times the height divided by 2. Okay. The centroid is drawn from the apex to the middle of the bottom part. Okay. Then the height from the bottom part is determined from is the formula equals is to the height divided by 3, 1/3 of the height. That will be the centroid of a triangle. Okay, and so if it is homogeneous, then the center of gravity will also be at that centroid. Let's say then we have a quarter area and semicircular area. This is a quarter area. For semicircular area, yeah, which has the area equals to pi times r squared divided by 2. Pi r squared is the area of the whole circle. If it is divided by 2, then it becomes the semicircle. The height from the bottom of the centroid or center of gravity, if it were uniform, equals to 4r divided by 3 pi. Okay, 4 times the radius, okay, sorry, divided by 3 times pi. If it were quarter, yeah, the height is still the same. The x is also the same, which is equal to 4r, 4 times the radius divided by 3 pi. So here the area is pi r squared divided by 4 because it is a quarter area. If we have an arc means just a line being bent, yeah, to form an arc. If it is semicircular arc, yeah, the perimeter equals to pi times r, yeah, the formula of the circular but divided by 2. Then the height of the centroid or the height of the center of gravity equals to 2 times r divided by pi, more or less here. If it is quarter arc, then the coordinate of the centroid equals to x, the x and y equals to 2r divided by pi. For a circular sector like this, yeah, this is means it is an area. The area is alpha times r squared, right? Alpha is the radian, yeah, the radian angle. Then the position of the centroid from the center of that circle, the x, yeah, equals to 2r sine alpha divided by 3 alpha. Okay. From where does this come from? Yeah, please refer to the solid mechanics textbook. The arc or mathematics or geometry textbook also. The arc of a circle, so it's a line, not an area. The x, yeah, the L here, the location of the center of gravity here equals to r sine alpha divided by alpha. Alpha here is the half of the angle, half of the radian sector, angle sector of that arc. If we have a semi-elliptical area, so ellipse basically is when the horizontal and the vertical axis are different. So the here x component will be at the middle, of course, while the y, or the height of the centroid, is equals to 4 times b. B is the shorter axis, divided by 3 pi, divided by 3 times pi. If it is quarter area, then the x here along the longer axis equals, the coordinate equals to 4 times a divided by 3 pi, while along the shorter axis is the center is 4b, 4 times b divided by 3 pi. If it is parabolic area, yeah, here, y, the coordinate from the flat part is 3h here, 3 times h, the height, yeah, from the flat line to the peak, to the apex of the parabolic line, 3h divided by 5. If it is semi-parabolic, so half of the parabolic, then the x is from the center is 3 times a divided by 8, while the y is equals to the parabolic area here, 3 times h divided by 5. Spandrel here is the, when we have a curve y equals to kx times n, yeah, the x-axis of the centroid here equals to n plus 1 divided by n plus 2 times a. A here is from from the center to the right part. And y, the height, equals to n plus 1 divided by 4n plus 2 times the height. Okay, so I think we will continue this in the next session.